Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Parallel supercomputing is in and of itself almost a branch of mathematical physics, now called extreme-scale computational physics. Without mathematics, computer science becomes computer faith. I had to be a research mathematician to be able to invent the new partial differential equations and the corresponding partial difference algorithms that I discovered. My contribution to mathematics was to discover how to execute them across a new internet. There were two things that I did with my data. First, I copied them from one processor to another processor, and I copied them via email messages. Second, I computed with them at the slow speed of 47,303 calculations per second per processor, and I did so to reach the aggregated speed that was for the first time faster than the speed of any vector processing supercomputer. Put differently, my contribution to extreme-scale computational mathematics did not reside on the processor that was not a member of an ensemble of processors. My contribution to mathematics reside on the processor that is a member of an ensemble of processors and also resides on the entire ensemble itself. Yet, my parallel processing experiment had to wait until the 1980s when 65,536 processors became available for me to experiment with. I said that a petroleum reservoir model that runs on 3 instead of on 4 forces is akin to driving your car on 3 wheels. And with the 4th tire deflated. The lesson that I learned is that you must be a polymath, not a mathematician, to solve the multidisciplinary grand challenge problem that is beyond the frontiers of arithmetic, algebra, and calculus. The reason I could move back and forth from the blackboard to the storyboard is that I am a research mathematician and a research physicist. I knew the 4 forces that define the second law of motion of physics when applied to oil fields, and knew that law forward and backward, and knew how to encode that law into a system of 9 coupled nonlinear, time-dependent, and 3-dimensional partial differential equations of calculus that governs the 3-phase flows of crude oil, injected water, and natural gas that is flowing across an oil field that is a mile deep and that is the size of a town. To solve the Philip Emeagwali equations that are my contributions to mathematics, and do so across a new internet that is a new global network of 64 binary thousand processors, demanded that I discretize the problem domain of the initial boundary value problem. To discretize the problem, I approximated continuous space with discretized space or a finite grid. My new system of partial difference equations of algebra are the discrete versions of my new system of partial differential equations of calculus that I invented. As a research mathematician that is also a research physicist and that is also a research supercomputer scientist, my interdisciplinary knowledge was the necessary tool that gave me the intellectual maturity that I needed to correct the century-old critical errors that I found in calculus textbooks that were written for the petroleum industry. Those errors in calculus found their way from the classroom to the petroleum reservoir simulator used by ExxonMobil Corporation. I should mention that when I discovered that new calculus, or the Philip-Emeagwali equations, I had to create new algorithms that led to new algebra that also codified the second law of motion of physics. Inventing an equation is like making your words a part of the Holy Scripture. The Philip-Emeagwali formula was not for the blackboard alone, nor was it for the motherboard alone. The Philip-Emeagwali formula was invented for parallel processing across my 65,536 tiny computers, or as many processors, that encircled a globe in the way the internet encircled planet Earth. The Philip-Emeagwali formula made the news headlines in 1989 and was highlighted in the June 20, 1990 issue of the Wall Street Journal. 11 years later, that Philip-Emeagwali formula was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential speech of August 26, 2000. The parallel supercomputer is a disruptive technology that gives tech companies some competitive advantage in their drive for market leadership. The roots of the story of how the fastest supercomputer was invented began several millennia ago and began when our ancestors had no computing aid. For millennia, our ancestors used their fingers and toes as their computing aids and had no mathematical symbols scribbled on their cave walls. For the last 100 years, the word computer was prefaced as human computer, analog computer, and electronic computer, digital computer, distributed computer, parallel computer, and supercomputer. A change in how we look at the computer was accompanied by renaming the computer. The paradigm shift in supercomputing manifested itself as a change in the name of the technology, such as changing from sequential processing that began with computing aids, such as the abacus that was invented 3,000 years ago, to the parallel supercomputer that became the world's fastest computer when I discovered it on the 4th of July 1989. Over the centuries, we changed the ways we counted. We changed from the table of logarithms to a mechanical calculator to automatic computers that used vacuum tubes. And then our computing paradigm shifted to transistors embedded in integrated circuits. On the 4th of July, 1989, I figured out how to record an increase in computing speeds and do so across a new internet that is a new global network of 64 binary thousand tightly coupled processors that were simultaneously solving the grand challenge problem that I chopped up into 64 binary thousand problems. That invention, called parallel processing, triggered a paradigm shift in how computers are designed and defined. That invention changed the way we look at the computer. The new computer changed from computing only one thing at a time to computing many things at once. In 1989, I was in the news because I figured out how the new computer can solve in one day a grand challenge problem that the old computer needed 180 years or 65,536 days to solve. It's impossible to fully describe how I felt the moment I experimentally discovered parallel processing. At a visceral and intellectual level, I felt like I was a part of human progress that was bigger than myself. My discovery of practical parallel processing felt like I caught a fish that was bigger than myself. My discovery of parallel processing was computing's equivalence of reaching the top of Mount Everest and being the first person to reach that summit. My invention is the subject of school reports because it is a contribution to the development of the computer. That invention redefined the word computer in the new definition for the 21st century. The computer is a machinery that is powered by an ensemble of up to billions upon millions of processors, with each processor akin to a tiny computer that shared nothing. I believe that our children's children could parallel process across their internet and do so to upgrade their 22nd century's internet to that century's supercomputer that should be a planetary-sized supercomputer. I invented a new internet that I theorized as the granite core of a new supercomputer. In 1989, I was in the news headlines because I figured out how to reduce 180 years of time to solution on one computer that was powered by only one processor to only 1 day of time to solution on a supercomputer that was powered by 64 binary thousand processors. My contributions to geology, mathematical physics, and supercomputing is this: I figured out how to compute faster and do so to discover and recover otherwise elusive crude oil and natural gas. Back in the 1980s, practical parallel processing was an uncharted territory of human knowledge and a new frontier without a map. The marriage of partial differential equations and massively parallel processing was pretty abstract to grasp, but amazingly powerful. In weather forecasting, solving the difficult to calculate primitive equations of meteorology tells the weather forecaster tomorrow's forecast, Back in the 1970s and 80s, to parallel process across an internet was the most complicated concept and the hardest area of computational mathematics. If you are the first person to parallel process and to solve the toughest math problems, you will be ranked as the world's smartest person. Back in the 1980s, 25,000 vector processing supercomputer scientists avoided this grand challenge problem and did so because it was ridiculously difficult to solve. The precursor to the grand challenge problem that I solved on July 4, 1989 was first posed in a science fiction story that was written on February 1, 1922. My contribution to physics was that on the 4th of July 1989, I discovered how to turn that science fiction called parallel processing that then 66-year-old Albert Einstein presumably read about in the January 11, 1946 issue of the New York Times, and how to turn that science fiction into a non-fiction that is the vital technology that makes the supercomputer super. That grand challenge problem that was at the crossroad where mathematics, physics, and supercomputing met remained unsolved for the 67 years onward of 1922. That grand challenge problem was unsolved until I solved it on the 4th of July, 1989.
Insightful and brilliant lecture.